Hello everyone, welcome to the second lecture of week 12. Today what we are going to do is again we'll continue direct stiffness method, the concept again. In the last class what we learnt is we tried to understand the concept of direct stiffness method through analysis of plane truss. We have not done the examples that we will be doing in the subsequent lecture, and today we will be doing the same exercise through analysis of beams. We will see what would be the form of the matrix, stiffness matrix for beams. Okay, again this is the slide which gives you the summary of displacement method. I showed this slide in the last class as well. Ideally what we want to do is we want to get this relation, right. Here are the degrees of freedom, that the stiffness matrix, and these are the nodal force vector. And if you recall what we discussed in the last class, and again the similar exercise we did in the displacement method while talking about slope deflection method and all. We have a beam, then we decompose the beam, we assume that each segment of the beam as fixed beam, and then we determine what are the fixed end moments and the corresponding stiffness coefficients. Okay. Now suppose let's consider this beam, what is shown on this slide. Now this beam has several span AB, BC, CD and DE, and the idea is we decompose the system into small subsystem for that, such that for each subsystem we have the information, we know the relation between force and displacement through stiffness, and once we know this relation, then we assemble all the subsystems to get the global system equation for the entire system. Now let's assume, what we do is let's take one span, any random span of this beam, and then see what would be the force displacement relation for that particular span, and similar force displacement relation can be obtained for any span. Okay. Now so let's take one span AB. So this end is fixed and this end is fixed. Okay. Now so the entire beam is now divided into small sub beams, and this is one such sub beam, one such small segment, and we are going to derive the force displacement relation for this segment, and similar force displacement relation can be obtained for all segments, and then we can assemble them. Okay. Now first thing is we need to suppose this is the point number 1 and this is the point number 2. Okay. Similar in the truss case also we have a point, and point number 1 and point number 2. We also have a global local coordinate which is x dash here, and this is y dash, this is y dash. We are talking about we can have also z dash, which is normal to this plane, but since we are talking about plane structure, we have only two coordinate axes, x dash and y dash. This is the local coordinate axis. Okay. Now let's define the degrees of freedom. As we know, any point in two-dimensional plane has 3 degrees of freedom, 2 translation and 1 rotation. In local coordinate system for a truss, only the axial translation is allowed. That's why in local coordinate system for each truss member we had 1 degrees of freedom at every point. So total 2 degrees of freedom for any member. Now in this case, since there is no such assumption that the force always has to be axial, there is no rotation, no bending takes place, we don't have such assumptions here. So ideally at every point we should have 3 degrees of freedom. In this case, translation in this direction, translation in this direction, and rotation. Translation this, and then rotation. Okay. Now to start with, we assume so here 3 degrees of freedom, 2 translation and rotation, here 3 degrees of freedom, total 6 degrees of freedom. In plane truss in local coordinate system, it was just 2 degrees of freedom per member. Now to start with, let us assume there is no axial deformation in this member. Okay. So axial deformation is neglected. Now, if we assume there is no axial deformation in the member, then what happens? Then the degrees of freedom that we will be interested in only at this point, it is the translation in this direction and the rotation at this point, translation in this direction and rotation at this point. Okay. So, first we will see for a beam there is no axial translation, axial deformation is allowed. We will derive the stiffness matrix by considering other 2 degrees of freedom per node, and then knowing the fact that when axial deformation is allowed, what the stiffness matrix, what is the form of stiffness matrix. We have already learned that in truss problem we can combine them to get when all degrees of freedom present. So, now the degrees of freedoms here are this. We have degrees of freedom is this, which is say which is degrees of freedom say 1. Okay. And then we also have, say this is E1, this is E1, E1 dash. Okay. And then we also have rotation at this joint. Rotation is shown by this double arrow, and this is U2 dash. Similarly, we have displacement translation in this direction, U3 dash, and again rotation at this point, which is shown by double arrow, U4 dash. Okay. So, there is no translation here, because for the time being we are neglecting the axial deformation. So, at every joint we have 2 degrees of freedom, one transverse translation in transverse direction and one rotation. Okay. Now, let us, similar to truss, first we consider the each degrees of freedom and then find out what are the corresponding stiffness coefficient. Okay. Let us first consider the degrees of freedom, 2 degrees of freedom at this joint, considering this end fixed and this end allowed to have the deformation as per the degrees of freedom. And next what we do is we will assume this end fixed and this end is allowed to move, allowed to deform as per the degrees of freedom we consider. Okay. So, first is let us take degrees of freedom E1, means this point, the point number 1, it translates in this direction, but there is no translation, no rotation takes place at this point, and there is no rotation takes place at 1. So, it is only one translation takes place at point 1. So, if it is, then actually your structure is initially like this. This is fixed, this is fixed. Now, what we do is we give a translation in this direction. So, the deflected shape becomes something like this. So, this is translation in this direction. Okay. And suppose this translation, the value of this translation is unit, it is U dash is equal to 1, this is 1, this value is 1. Okay, and this value is 1. Now, if you recall your slope, the lectures in slope deflection, when we discussed slope deflection method, we actually solve these small problems. If we have a fixed beam and giving axial transverse deflection or support settlement in a particular direction, what are the forces and moments generated at the support. So, we have already determined these values, and let us just write those values. So, we have a moment generated at this point, and the value of this moment will be 6 EI by L square, where L is the length of the beam. We have already derived this value. If you please refer to the lecture when we discuss slope deflection method. And for this there will be a force generated reaction force generated in this direction, and that value will be 12 EI by L cube. Okay. And similarly, there will be a reaction generated in this direction, and which is value will be 12 EI by L cube, and then a moment generated will be in this direction, and this moment value will be 6 EI by L square. Okay. So, what you can do is you have a fixed beam which is where you have a support settlement of unit support settlement at a particular point, at a particular joint, and then because of that support settlement, what would be the support reactions, what would be the reactions at the moment generated at the support. You can use any method to determine these values, and since you know these methods, several methods to determine these values, we are not going to derive these values once again. Okay. So, these are the corresponding reactions you get. Okay. Now, similarly, let us give unit rotation at this point. Now, this is for unit translation. Now, let us give unit rotation at this point. So, originally your structure is like this, the member is like this, which is fixed here, this is fixed here. Then we give an unit rotation at this point, and if we give an unit rotation, then this is unit rotation, and this actually support becomes like this. Okay. And this value is unit, this value is 1. So, again we have a fixed beam, and then one end you give a unit rotation, or a propped cantilever beam, one end the propped end you give an unit rotation, then what would be the corresponding moment and corresponding reactions at the support, that we can obtain by any methods that any method that we have learned so far. And if we give an unit rotation here, then the corresponding forces will be, we have a vertical force here, this vertical force will be 6 EI by L square, and then there will be reaction here which is again 6 EI by L square. To satisfy the equilibrium, there will be in opposite direction, and there will be a moment here, and this moment will be 12 EI by L, and then corresponding moment here will be, this value will be 6, this value will be this value will be, there is this value will be 4 EI by this okay, just 1 minute, this value will be 4 by this 4 EI by L, 4 EI by L. This reaction will be this reaction, just 1 minute, this reaction will be 6 EI by L square, and this value is be 4 EI by, this value will be 4 EI by L. Okay. Now, you see, so what we have done is we consider there are 2 degrees of freedom at each joint, here translation in this and rotation of this joint, translation and rotation at this joint, U1 dash, U2 dash, U3 dash, U4 dash. Now, we are considering each degrees of freedom separately and checking for if the member is allowed to have that degree, allowed to have the deformation as per the degrees of freedom, as per the chosen degrees of freedom, what would be the corresponding moments and what would be the corresponding reactions generated at the support. So, this is for translation at joint 1, this is for rotation at joint 1. Similar exercise we can do for translation at joint 2 and rotation at joint 2, and if we do that, then what we have is something like this. Now before, suppose again this is the structure. This is a structure, and now this end was actually fixed. Now, this is joint number 1, joint number 2. Now, this joint is allowed to have translation in this direction, and if it translates like this, then the corresponding deflection will be like this. So, this will be, this is unity, and then corresponding translation of other joint will be like this. If you have similar structure, this end is fixed, this end is originally fixed, then this end we have unit rotation, and this unit rotation will be this unit rotation, and corresponding support will be like this, and this is unity, this is 1. And if we have this, then also we have corresponding reactions and moment, and those values will be like this. And for this we have a reaction force here, which is 12 EI by 12 EI by L cube, and corresponding reactions here will be 12 EI by L cube, and this will generate a moment in this direction, and this moment will be 6 EI by L square, and corresponding moment in this direction it will be 6 EI by L square. Okay. Now, similarly we can have a reaction force and moments here. Reaction force will be 6 EI by L square, and then this will be 6 EI by L square. So, you can please verify these values, and we are not deriving this value because we have done that, and you already know how to do that. Okay. So, now we have this, right. Now, next what we can do is, you see, what if you remember that for in the case of truss we had 2 degrees of freedom total at every member. In local coordinate system we have 2 degrees of freedom. Now, that is why for member stiffness matrix, the size of the member, size of the stiffness matrix and the local coordinate system were 2 by 2 matrices. Okay. Now, here we have 4 degrees of freedom, 2 here and 2 here. So, naturally the degree size of the stiffness matrix will be 4 by 4. Okay. Now, if you remember, this is the stiffness matrix. If we take this is a stiffness matrix, consider this is the stiffness matrix for this member. Now, K11 is essentially associated with it relates the force at force corresponding to first degrees of freedom 1 and the degrees of freedom 1. K12 is actually the force in the direction of degrees of freedom 1 due to degrees of freedom 2, and then force K13 is the force in the degrees of freedom 1 due to degrees of freedom 3. So, similarly, now you see here this is the force, this is degrees of freedom 1. So, this is the force in degrees of freedom 1, and this force is generated due to U1 dash. So, this is essentially your force in the direction of degrees of freedom 1 due to degrees of freedom 1. Okay. Now, what is this force? This is essentially, this is in degrees of freedom 2, because that is the rotation U2 dash. Okay. Now, this force generated in the direction is corresponding in the direction of degrees of freedom 2, but this is caused due to degrees of freedom 1. So, therefore, this is in the direction of degrees of freedom 1 due to degrees of freedom 1. So, this will be essentially K11. Okay. Now, this is in the direction of degrees of freedom 2, but due to degrees of freedom 1. So, this will be K12, and then similarly this will be, this is in the direction of degrees of freedom 3, but due to degrees of freedom 1, because this force is caused due to the translation U1 dash. So, this will be K13, and similarly this will be K14. Okay. Now, look at this. Now, here it will be this is now degrees of all the forces here generated due to degrees of freedom 2. Now, this is in the direction of degrees of freedom 1, but due to degrees of freedom 1. So, this will be K21, and this is in the direction of degrees of freedom 2 due to degrees of freedom 2. This will be K22, and this is in the direction of degrees of freedom 3, but due to degrees of freedom 2, this will be K23, and this will be K24. Okay. Now, our sign convention is this direction is positive, this direction is positive. So, K11 will be 12 Bi by L cube, K12 will be 6 EI by L square, K13 will be minus 12 EI by L cube because it is in opposite direction, and K14 will be 6 EI by L square. Similarly, this will be K21 will be 6 EI by L square, it will be 4 EI by L square, and this will be minus 6 EI by L square, and this will be 12 EI by L. Similar thing we can have for member for degrees of freedom 2 as well, and similar expression we will get. Okay. Now, if we put that in a matrix form, then this matrix will look like this. Okay. So, this is degrees of freedom 1, this is degrees of freedom 2, this is degrees of freedom 3, this is degrees of freedom 4. This is 1, this is 2, this is 3, and this is 4. You see, now this gives you the this is stiffness matrix. The stiffness is essentially force for unit displacement. So, this gives you the force due to degrees of freedom 1. So, 12 Vi by L cube, which we have already obtained 12 Vi by L cube. This gives you force in direction in degrees of force F1 due to degrees of freedom 2, which is 6 Ci by L square, which we already obtained 6 Ci by L square, and similarly this. Now, so if we substitute that in a matrix form, you get like this. And another important thing, please look at this. This matrix is symmetric matrix, means the force generated in direction 1 due to degrees of freedom 2 is equal to force generated in direction 2 due to degrees of freedom 1. That we can check here also. Force generated in degrees of freedom 2 due to degrees of freedom 1 is 6 Ci by L square, and force generated in degrees of freedom 1 due to degrees of freedom 2 is 6 Ci by L square. This and this are same. Okay. So, this we already discussed during in a reciprocal, when we actually discuss reciprocal theorem. It is one demonstration of that. Okay. Now, this gives you the stiffness matrix of a beam segment when we neglect the axial deformation. Now, similar stiffness matrix we can obtain for all the beam segments, and then we can assemble them. Now, as far as beam is concerned, you see, this is our local coordinate system, and our global coordinate system is also, if you take like this, then local coordinate system and global coordinate system, they are same. If they are same, the stiffness matrix that you obtain for local coordinate system, the same stiffness matrix you can obtain for that beam segment for global coordinate system as well. So, this will give you the global coordinate stiffness matrix for a given member for global coordinate system. Similarly, you can have the stiffness matrix in global coordinate system for all the member and then assemble them. And how to do that assembling and all, when we do actually some numerical example, we can see that. Okay. Now, what happened if we, so these we obtain when there is no axial deformation considered. Now, if we allow some axial deformation, then what happens? Now, suppose the axial deformation is also allowed. So, what happened? This is a beam segment, this is a beam segment, and this is your point number 1, this is point number 2, and degrees of freedom are this is axial deformation, this is U1 dash, and this is U2 dash, and this is U3 dash. Similarly, at this point you have U4 dash, U5 dash, and then rotation here is U6 dash. Okay. So, when there is U1 dash and U4 dash, there is no U1 dash and U4 dash, then stiffness matrix is this, isn't it? So, these stiffness matrix correspond to this becomes, this is for translation, means second degrees of freedom. See, now we are talking about if we consider axial deformation, and this is for rotation, which is now 3, and this is for again translation at this point, which is now 5, and this is rotation at this point, which is now 6. Okay. And similarly, this is become 2, 3, 5 and 6. Okay. So, this is when we consider axial deformation. Now, here we have to insert column number 1 corresponding column rows and columns corresponding to first degrees of freedom and the fourth degree of freedom. Now, we already know from truss that if now this we can decompose, this entire problem we can decompose like this. This can be decomposed into two problems. Which one is this plus another problem this, where this is node number 1, node number 2, this is node number 1, node number 2. Now, here you give only these degrees of freedom u2 dash and rotation u3 dash, okay. And here you give only u5 dash and rotation u6 dash, and here you give only translation u1 dash and u4 dash. So, since linear superposition is allowed here, so we have just now the beam is undergoing deformation this plus undergoing deformation gives you the total deformation of this. Okay. Now, for this we have just now obtained the stiffness matrix, and for this it is very similar to truss. We know the stiffness, what is the stiffness matrix. For this stiffness matrix is this corresponding to degrees of freedom. Now, degrees of freedom are identified as 2, 3, 5 and 6, and for this stiffness matrix we have already obtained, and that stiffness matrix, if you remember, that stiffness matrix was like this: AE by L, AE by L, this is becomes 1 minus 1 minus 1 1. It is for truss, and this is degrees of freedom 1, this is degrees of freedom 4, this is 1, this is 4. Okay. Now, what we need to do is we have this stiffness matrix which is for this beam, and we have this stiffness matrix which is for this beam, and we have to combine them. How do I combine them? We will combine like this. We can we write the degrees of the 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. Okay. And then this become this. This become this. Okay. Now, so okay, this is 1 1, this is 1 2, this is 1 3, 1 4, 1 5, 1 6. Okay. Now, what is 1 1? 1 1 is AE by L, and 1 4 is minus AE by L. So, 1 1 will be AE by L, 1 4 will be AE by L. And what is 1 2, 1 3, 1 5, 1 6? You see 1 3, these are all 2 3 5 6, 2 3 5 6, there is no 1 here, there is no 2 3 5 6 here. So, these all become 0. Okay. Similarly, this will be 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. What is 2 1? 2 1 is there is no 2 1 here, there is no 2 1 here. So, 2 1 becomes 0. What is 2 2? 2 2 become there is no 2 2 here, there is 2 2 here. 2 2 is 12 EI by L cube. So, this become 12 EI by L cube. Okay. So, similarly, if we put every element in their corresponding cell, the stiffness matrix that we get is this. Okay. So, this will be for 1 2 3 4 5 6 1 2 3 4 5 6. This is element stiffness matrix, which is 6 by 6 stiffness matrix, because you have total 6 degrees of freedom per element. Now, once we have similar stiffness matrices, member stiffness matrices for all the members, then we assemble them and get the final global stiffness matrix, which and then we can write Ku is equal to F in this form. and then we have to solve these equations, and how to assemble them and how to solve them, how to calculate the the load vector f, that we can discuss when we actually solve some examples. Okay. So, as far as the theory is concerned, it is a I mean, it is not even a brief introduction what we have done so far in last week, last class and this class. It is not even no, you can see it is a small trailer of the entire movie, which is direct stiffness method. Okay. The idea here has been to tell you that there is a method which is based on the concept that we have learned in the first 11 lectures, but the method is not method can be translated into computational code, and from there there is more advanced method for analysis of structure can be developed. The idea has been that if we really want to learn direct stiffness method, then there is a separate course, and there is a book on direct stiffness method, and you have to take other course or learn it properly. This week is just to take you to the is a transition from your basic level course to the more advanced level course, and in that perspective, whatever we have discussed in the last class and this class, probably it can motivate you to learn the method in a more detailed way. So, next few classes, what we do is whatever the concept that we learn of matrix method of analysis as direct stiffness method, we will solve 3 problems. One is for truss, one is beam, and one is frame. Truss is where only axial deformation takes place. In the beam, we will neglect the axial deformation. We will assume that there are 4 degrees of freedom, 2 degrees of freedom per joint, a transverse direction and the rotation. And then frame, where we will combine both, where axial deformation also is a degrees of freedom. So, in that case, there will be the stiffness matrix will be 6 by 6 per member. Okay. So, next class will be direct stiffness method analysis of truss. Okay. So, in the next class, thank you.